तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Good morning. Last two lectures we have been working with the wave equation, and today I am going to continue that and go a little bit more into detail. So, let me remind you what we had done last time. We had taken a special problem where we assume the electric field is pointing along the x direction, the magnetic field is pointing along the y direction, and we assume that the electric field along the x direction was some function of z and t. That is, it did not vary if you moved in x, it did not vary if you moved in y, but it did vary if you moved in z. Similarly, hy was some other function of z and t. And last time we worked out and found that if you solve this problem, you find that the electric field Ex is actually a function of a very specific form. It is the sum of one arbitrary function depending on z minus Ct and another arbitrary function z plus Ct. This f and g are completely up to us, they can be anything at all, where c was equal to 1 over square root of mu naught epsilon naught. This is in vacuum. I did not prove it, I gave it to you as an assignment, but you can show that the equation satisfied by Ex, namely del squared Ex del z squared minus 1 over c squared, well I should not say 1 over c squared, minus mu epsilon del squared Ex del t square equals 0, this equation we have derived. Exactly the same equation can be derived for Hy. I did not prove it, I left it to you to work out. So, it is the same equation in both cases, therefore, it is the same solution. So, you will also end up with Hy is equal to some other function f tilde of z minus Ct plus g tilde of z plus Ct. So, we have two solutions. Of course, there are two solutions in terms of 4 arbitrary functions, which means that we have tremendous amount of freedom in specifying what we want to specify. Now, in addition, what I also did last time was I said, supposing this is x, this is y, this is z, supposing the electric field has a certain shape, that is, it points along the x axis, there is a triangular profile plus there is a rectangular profile. you should imagine that both of these are pointing along x. Now, I have drawn it only on the z axis, but really when I draw this arrow, it means that for all x and all y it is the same electric field, because the electric field depends only on z. It is uniform in x and it is uniform in y. So, now take this electric field and suppose that this part of the electric field was dependent on z minus C t and this part depended on z plus C t. I think I have inverted the case. The rectangle was actually here. Now, what we saw was that if this was z plus C t and that was z minus C t, this triangle moves in the positive z direction as you vary time, and this rectangle moves in the negative z direction. They meet, and when they meet, superposition means that you end up with complicated shapes, but after sufficient amount of time this triangle would have reached up here and this rectangle would have reached up here, down here. So, you would have this triangle moving up and this rectangle moving down, and this is why they are called waves. They move. These are disturbances that are not like Coulomb's law at all. It is an electric field. So, you are used to electric fields which are due to charges, and therefore, they stay put. If you put a charge somewhere, the electric field around that charge is fixed to the charge. But this electric field is not fixed to a charge, it is just moving. There is no charge in the derivation. When we derived this, we assumed there is no charge density, there is no current density. You just had a disturbance, and the disturbance self consistently just keeps moving. So, it is a very different object from what we have seen earlier. Coulomb's law is for fixed static charges. These kinds of moving structures are coming out of Maxwell's equations, the generalized Ampere's law. Now, what I am going to do is to relate E x and H y. Last time I just said that E x and H y have the same shape, and that is reasonable because E x is connected to H y through Faraday's law and Ampere's law. So, if there is a triangular E x, there is something, we do not know what, but there is something at the same z for that t, because otherwise you could not have curl of E being related to del B del t at the same point. You could not have curl of H related to del D del t at the same point. So, at the same z where there is electric field, there must also be magnetic field, and if this electric field is moving in time like this, so too must the magnetic field, and if this electric field is moving backwards in z, so too must its magnetic field. So, we can see that there is a correspondence between whatever is the forward moving disturbance due to E and the forward moving disturbance due to H, because Faraday's law connects them up, Ampere's law connects them up. Similarly, there is a connection between the backward moving disturbance G and the backward moving disturbance G tilde. Let us put all of this a little more solidly. So, what I am going to say is that let z minus C t be equal to u, z plus C t is equal to v, all right, and I am going to assume that E x is some function of u only, there is no v in it, and I am going to try and find out what is the kind of H that comes out of such an electric field. So, that corresponds to considering only the triangle part of the disturbance. I am not doing anything terrible by assuming this, because I can always solve this problem. Then I can solve a problem where Ex is equal to some g of v, and then I can add up the two solutions. And since the wave equation is linear, it means that if I have solved this problem and I have solved this problem, I have solved the full problem. All right. This is very much like your pendulum problem, x double dot plus kx equals 0. Well, I can study x, let us put k squared, cos kx, I can study x equals sin kx, I can study their properties, and then I can write the general form, which is a cos kx plus b sin kx. So, just in the same way, I can look at just E equals f u, and I can look separately at E equals g of v, and then I can add up a linear combination of these two. There is no need to add up linear combinations, because each of these is an arbitrary function. So, it includes a scaling factor as well. So, let us see what we get. So, I am going to use this form, Ex is equal to f of u. Now, what is Faraday's law? Faraday's law tells us curl of E is equal to mu naught del H del T. I know that this is in the y direction, so I need the y component of this. So, the y component of curl of E is going to be del del z of Ex is equal to mu del H y del T. So, minus sign, because it is Faraday's law. What is Ampere's law? Curl of H is equal to plus epsilon naught del E del T. Now, E is in the x direction, so del E del T is in the x direction. So, I need the x component of curl of H, which is minus del del z H y is equal to epsilon naught del E del E x del T. I have derived these several times, so you should be quite comfortable with it. Now, I have assumed E x is f of u, which is f of z minus c t. So, I can substitute for the E x portion. So, what do I get? I get that minus mu naught del H y del T is equal to del del z of E x, which is du df du, because du dz is 1. What do I do? What do I get here? I get minus del H y del z is equal to epsilon naught times del E x del t. So, when I take del u del t, I get a minus c times df du. Now, as I said, H is really f tilde of u plus g tilde of v. But if you look at these expressions, you find that del H del T and del H del Z are functions of u only, they are not functions of v at all. You can see that the right hand sides have constants multiplying functions of u, which means H y cannot depend on v. This is not saying anything surprising, it is simply saying that if the electric field disturbance is moving in this way, the magnetic field disturbance must also move in the same direction. Otherwise, supposing the magnetic field disturbance was moving the other way, then what would happen? After a certain time, this triangular disturbance would have reached here, but the magnetic field disturbance, whatever its shape, was moving in the opposite direction. So, it would have reached somewhere here, but you can't have Faraday's law connecting curl of E here to del H del T here. Curl of E is related to del H del T at this point. So, whatever direction the electric field is moving, magnetic field must move in the same direction. So, it means there is no G of V. So, I now know that H y is F tilde of u. So, I can substitute for these derivatives as well. So, what do I get? I get minus mu naught del F tilde del T. So, when I take del T, I get a minus C d F tilde du is equal to df du. This one says minus del z does not give me a factor, df tilde du is equal to minus C epsilon naught df du. Now, actually both of these expressions are saying the same thing, because C is equal to 1 over square root of mu naught epsilon naught. So, if you look at this side, this says mu naught C, which is equal to square root of mu naught over epsilon naught, because C is 1 over square root of mu naught epsilon naught. Mu naught over square root of mu naught epsilon naught is going to give me a square root of mu naught in the numerator, and this epsilon naught gives me an epsilon naught in the denominator. This term C epsilon naught is going to be epsilon naught over square root of mu naught epsilon naught, which is going to give me square root of epsilon naught over mu naught. Now, this is on the left hand side, that is on the right hand side. So, if I bring everything to the right hand side, I get one equation out of this. It says df twiddle du is equal to square root of epsilon naught over mu naught df du. This is just a constant. This is the u derivative of the electric field. This is the u derivative of the magnetic field. Now, if you integrate both sides with u, what will you get? You will get f twiddle is equal to this factor square root epsilon naught over mu naught times f plus constant. The constant does not matter, we are interested in moving objects. So, a constant is Coulomb's law. So, we will not worry about constants. We are only interested in disturbances of the type which give us waves. So, it tells us that whatever shape you take for f, it can look like a man, it can look like a triangle, it can look like a square, it can look like anything at all. The same shape is there for the magnetic field. It is scaled by a factor epsilon naught over mu naught square root, but otherwise magnetic field and the electric field are the same function. They are moving in the same direction, and not only that, they are even the same function. So, if you draw it properly, the magnetic field points in the y direction, and it points that way. So, the electric field points in this direction, magnetic field points in that direction, and they both move together. It is a very important thing to understand that in Coulomb's law, charges were the source of electric field. So, since the charges were stationary, electric field was stationary. In this case, if you look at these equations, actually what they are saying, let us look at this kind of equation. What they are saying is that the source of the electric field is the magnetic field, the source of the magnetic field is the electric field. So, it means that the electric field causes the magnetic field, which in turn causes the electric field, but there is a phase shift that is going on, and because of the phase shift they are forced to move in order to keep in step, and that motion is nothing more than the speed of light. This is 3 into 10 to the 8 meters per second. I think it is very important to understand this point, that I have not made any assumption about what this shape was. This is arbitrary, it can be any shape at all, and whatever shape I assume, magnetic field will take the same shape. Now, everything I said which was for f of u can be repeated for g of v. If I do that, what I will get is that this df du will become dg dv, dg dv, and I will then be forced to throw out f and keep g tilde, and I will write now equations connecting g tilde and g. I will get once again the same set of two equations which are identical, and they will again say the same thing, and I will get g tilde is square root of epsilon naught over mu naught g. Once again, for an arbitrary shape in electric field, I get the same shape in magnetic field scaled by a factor. So, ultimately my picture looks like this. This is my z axis, y axis, x axis. I have my electric field, this part of the electric field is moving in the positive z direction, this part of the electric field is moving in the negative z direction. Corresponding to this electric field, I have a magnetic field along the y direction, and corresponding to this also I have a magnetic field pointing in the y direction, and this magnetic field is Hy of z plus Ct, and this magnetic field is Hy of z minus Ct. So, both these together move in the positive z direction, both these together move in the negative z direction, and if they happen to cross each other, which is very possible, as in time they are moving in opposite directions, so they will go through each other. All that will happen is, at every point the local electric field is the sum of these two fields. So, they will distort, the shape will look funny for a while, they will go right through each other, but once they have come through each other, once again you will get back this shape, but down here moving further down, and this shape up here moving further up. Now that we have worked out one dimensional problem, let us do a more honest job of the mathematics. We had the vector relations curl of E is equal to minus del B del T, and we had curl of H is equal to, I am ignoring currents and charges, so I do not have the J, del D del T. Now, I want to do exactly what I did earlier. What I did was, I took this equation and notice this had a time derivative, but I needed a space derivative. So, I took a space derivative of this equation in order to use this to eliminate B. That is what I did for the 1D case. So, I am going to do the same thing. I am going to take a space derivative of this equation so that I can eliminate this. But which space derivative do I need? I need curl of H. So, I need to take curl of this, which means I will have to take curl of the whole equation. Curl of E is equal to curl of minus del B del T. I have just taken this equation and taken its curl. This is acting on x, y, z, this is acting on time. So, they are independent operations. So, I can commute them. So, I get minus del del T of curl of B, but B I am going to write as mu H. So, minus, I will pull the mu out and H. So, I have written B as mu naught times H, but I know what curl of H is. So, I can write this as minus mu naught del del T of epsilon naught del E del T. So, I am following exactly the same procedure I followed to get the solution in the 1D case, or to get the equation in the 1D case. So, finally, I can write down an equation. The equation says curl of E is equal to, there was a minus here, yes. So, minus mu naught epsilon naught del squared E del T squared, and this is the 3D equivalent of the 1D equation, except that there is some very nasty business going on here. This does not look like del squared del z squared of Ex, which is what we had in the 1D case. This was there, but this one does not at all look like what we had earlier. So, we need to do some more work here. We know that at least in the 1D case it simplified. We can try and see if it simplifies even in the 3D case. Well, I have taught you the tricks of how to simplify such expressions. Curl of E can be written as epsilon I j k unit vector along I, derivative along j of curl of E along k. That is what a curl is. It is the cross product of the gradient operator and the function you are taking the curl of. But this itself is a curl. So, I can write it as epsilon I j k unit vector along I, derivative along j of epsilon k l m. I am introducing two new dummy variables L and M, del del x l E m. This is what is the kth component of curl of E. You would normally have an E sub k here, unit vector along k, but I have taken the dot product of that and the and this operator. So, the unit vector has got absorbed. So, you just have the kth component. So, I can write this out. It is epsilon I j k epsilon k l m E sub I, and I have del square del x j del x l of E m. if only this J and L were both equal, then this is beginning to look a bit like del squared del z squared of Ex. We have to now work on this piece. As I told you, epsilon ijk only cares about cyclic or anticyclic. That is, you can write your circle, put 1, 2, 3. If ijk involves going clockwise, it is 1. If ijk involves going counterclockwise, it is -1. So, I can always, if I have got 1, 2, 3, I can write 3, 1, 2. Both of them involve going the same direction. So, I can write this down as epsilon kij epsilon klm of Ei del square del xj del xl em. Now, kij must each be different, klm must each be different, otherwise these expressions are 0, which means either I equals L, J equals M, or I equals M, J equals L. If I equals L and J equals M, both of these are clockwise or both of these are counterclockwise. In one case it is 1 squared, in the other case it is -1 squared. So, both ways this becomes plus. So, I will try I equals L, J equals M. So, E sub I del squared del xj del xi of Ej, because I is equal to L, J is equal to M, minus, because if I is equal to M and J is equal to L, one of them is clockwise, one of them is counterclockwise. So, that is 1 into -1. So, minus. So, I is now M, J is now L. Ei del squared del xj squared of Ei. Now, we need to make sense of this. It is equal to Ei del del xi acting on Ej del xj minus del squared del xj squared acting on Ei. I have just collected terms. So, del del xi I have combined with the Ei, del del xj I have combined with the capital Ej. Similarly, here the Ei and the capital Ei have combined together. But each of these is a vector operation, and let me write down that vector operation. This is gradient and this is divergence of E. So, it is gradient of divergence of E minus this is del squared acting on vector E. It is as simple as that. So, I can reduce the wave equation to a simpler form. The simpler form is, let me rewrite the equation itself, curl E is equal to minus mu naught epsilon naught del squared E del t squared. This curl E became gradient of divergence of E minus del squared E is equal to minus mu naught epsilon naught del squared E del t squared. Now, I am assuming we are working in vacuum, and we have already assumed divergence of D is equal to 0, no charges. D is nothing but epsilon naught E. So, divergence of E is also 0. This goes away, which leaves us finally with the equation that is the generalization of the 1D problem. Del squared E minus mu naught epsilon naught del squared E del t squared is equal to 0. supposing the electric field depended only on z, then this del squared is del squared del x squared plus del squared del y squared plus del squared del z squared. But if E depended only on z, only this term matters, these two would be 0, and that would give me an equation that said del squared E del z squared minus mu naught epsilon naught del squared E del t squared is equal to 0. And if I further said E is nothing but E x along x, this is the equation we got earlier. So, this equation now includes this equation as a simple special case. What are the kinds of solutions you get for this equation? Before I discuss that, let me go back to the 1D problem. Let us graph a little bit more. I had drawn x, y, and I had said, let me guess that the electric field is in the x direction and the magnetic field is in the y direction. And from that I managed to get a solution. Now, calling this x and calling this y is pretty arbitrary. I could just as well have said electric field is in this direction, in which case I should have got the magnetic field in this direction. After all, if I rotate by 90 degrees, it should not really make any difference. So, I am not restricted to talking about electric field along x. I can also talk about electric field along y, and to be honest, I can talk about electric field along z, except it would not move in the direction z anymore. So, I could write an electric field that was partly in the x direction and partly in the y direction. Let me do that. I am going to assume I have a triangular electric field in the x direction which I know that means I have a magnetic field that is in the y direction. Let us say that I also have an electric field that is in the y direction. In that case, my magnetic field would be in the minus x direction. So, this is E x of, let us say, z minus c t. This is, I will use that chalk, h y of z minus c t. This is E y of z minus c t, and this is h x with a minus sign, minus h x of z minus c t. Both of these solutions are valid, and they both will travel in the positive z direction because they depend on z minus c t. You can have two more waves which will depend on z plus c t, one of which has E x and the other has E y. And these different directions of E x and E y are quite arbitrary, because as I said, choosing what is the direction of x and direction of y is something that we do as scientists or as engineers. The wave does not know what is x, what is y, and what is z. We have arbitrarily said the direction in which the wave is moving is called z. But the direction of the x of the electric field could be anything, and in fact is anything. In general, electric field will neither point along x nor along y. It will point along some general direction. But luckily, if we had these two kinds of solutions, then we can write down the full solution. We can say the electric field vector as a function of z minus Ct is going to be equal to some function f of z minus Ct along the x direction plus some other function. I am going to call it g, even though last time I was using g for z plus Ct. Here I am running out of symbols. G of z minus Ct along the y direction. Now, this is in general a vector field. This is the x component, this is the y component. So, if I have specified the x and y component, I have more or less specified everything. I could specify a z component, but if I specify a z component, as I will show later, the wave cannot travel in the z direction. So, by knowing the electric field along x and by knowing the electric field along y, I have covered all possible directions of the electric field, because the component along x and the component along y, if I show in the x y diagram, I will have some component along x, some component along y. I can vectorially add, and I will have a component in a general direction. So, this is a way of solving the full problem for any direction of the electric field whatsoever. I do not have to solve an infinite number of problems, I just solve two problems, a problem along x and a problem along y. Once I have done that, I have got the components, and therefore, I can build up any electric field at all. These components, the components along x and y, they are called polarizations. That is, I can find a solution where the electric field is along x, magnetic field is along y, and that will be called an x polarized wave. But I could also find a wave where the electric field points along y, magnetic field points along the negative x direction, that will be called a y polarized wave. I could actually also find a wave where the electric field pointed neither along x nor along y, but pointed, say, in this direction. In which case, the magnetic field would neither point along y nor along minus x, it will point in some intermediate direction, and it will look like that. But that wave in fact can be broken up into a combination of this wave and this wave, because any general direction of the electric field can be broken up into component along x and a component along y. Now, that is a very important idea when we come to this equation, because you see this equation is a more complex equation than the previous equation. I will write the previous equation for you to look at. That equation was del squared E x del z squared minus mu naught epsilon naught del squared E x del t squared is equal to 0. This part is the same. This del squared now is del squared del x squared plus del squared del y squared plus del squared del z squared. So, it is already a little more complicated, but the real increase in complication is here. This is a vector, which means it is E x x hat plus E y y hat plus E z z hat. Now, that is why we did a lot of algebra and got rid of this particular form. This is also a wave equation, this is also a wave equation, but this particular wave equation looks quite nasty. We do not quite know what to do with it, whereas this one looks sufficiently familiar to us after looking at this equation that we feel it is almost like the same equation. Well, there is one way of looking at this equation that makes it simpler. What we can do is we can say I will take this equation and write it as 3 equations. It is a vector equation. So, the way I will write it is I will say it is unit vector along x of del squared E x minus mu naught epsilon naught del squared E x del t squared plus unit vector along y del squared E y minus mu naught epsilon naught del squared E y del t squared plus unit vector along z del squared E z minus mu naught epsilon naught del squared E z del t squared, whole thing is equal to 0. I have just written it out. This has an E x x hat plus E y y hat plus E z z hat. So does this. So the unit vector along x is a constant. So it is not affected by del del t, it is not affected by del square. So I can pull it out. So I have collected all terms with x hat in it, all terms with y hat in it, all terms with z hat in it. But this is a vector equation, and if a vector at any x y z is equal to 0, it means that the x component of that vector is 0, the y component of that vector is 0, and the z component of the vector is 0, which means each of these brackets is separately 0. They can't, I mean I can't do anything in this bracket that could make this bracket 0. I can't do anything here that could make that 0. Each of them must separately go to 0, because that is what it means to say the overall thing is 0. So that allows me to simplify things a great deal. Instead of having a very complex vector equation, I now have 3 scalar equations. The 3 scalar equations are del squared E x minus mu naught epsilon naught del squared E x del t squared equals 0. That came from setting this to 0. Then I have del squared E y minus mu naught epsilon naught is equal to mu epsilon naught del squared E y del t squared. That came from setting this to 0. And finally, del squared E z minus mu naught epsilon naught is equal to 0. So I now have 3 equations in 3 scalar fields, and in fact I can see a very familiar equation here now. If only I could get rid of the x and y dependence, I have gone back to the 1D problem. And I have this equation which is now telling me that the y component of the electric field obeys the same equation as the x component, and in fact the z component obeys the same equation as well. Now I am going to simplify, because the whole point of this was not to do a very general analysis, it was to help us understand something very simple. Supposing the vector field E, which is a function of x, y, z and t, is only a function of z and t. It does not depend on x, does not depend on y. Then these equations are going to simplify. I will just write them in place. So, I get 3 equations. The 3 equations are del squared del z squared of E x minus mu naught epsilon naught del squared E x del t squared, similarly E y, similarly E z. Now, these 2 equations we are quite familiar with, but let me write down the corresponding equation for h also. It will be del squared del z squared of h x minus mu naught epsilon naught del squared h x del t squared equals 0, del squared h y del z squared minus mu naught epsilon naught del squared h y del t squared equals 0, del squared h z del z squared minus mu naught epsilon naught del squared h z del t squared equals 0. So, I have 6 equations, and I would like to know what kind of solutions I can get out of these 6 equations. Clearly, from what we have understood of the 1D problem, we know that E x has a preference for h y, and we can guess that E y has a preference for h x, which makes a question mark as to what these 2 are doing. But we have to get these relations out now out of Faraday's law. So, we have curl of E is equal to minus mu naught del h del t. Now, curl of E is x hat, y hat, z hat, 0 0 del del z, because I do not have del del x, I do not have del del y, E x, E y, E z, which is equal to mu naught times h x x hat plus h y y hat plus h z z hat. Now, if you look at this curl, you can see that there are 2 zeros here. So, what that means is, if I take the x component, so let me write down what this will be equal to. It is x component times del del y is missing. So, I do not have this term, minus del del z of E y. The y component has del del z of E x minus del del x is missing. So, this does not happen, and the z component requires del del x or del del y, both of which are missing, 0. So, there is no h z. The curl of E is linked to h x and h y, and how is it linked? H x is connected to del del z of E y, h y is connected to del del z of E x. Now, we can write the same equation for Ampere's law, except for a change in sign and this epsilon naught, it is the identical equation. So, it is going to tell us that E x is related to del del z of h y, E y is related to del del x del del z of h x. So, once again we find there is no z component. So, if we think of these waves as being sources for each other, there is no source for the z component. even though we have this equation here, we have no way of connecting up this z component to anything else. These kinds of waves can exist, but they cannot exist in vacuum. They can exist provided we have a medium, and we may look at that later on. And those kinds of waves are what are called compressive waves, and they are waves where the field is along the direction in which it is moving, because if you have variation only in z, it means the solutions are going to be z minus Ct and z plus Ct. The wave is moving in z and the fields point along z. Those kinds of solutions are very rare, they cannot exist in vacuum. In vacuum, what you can have are Ex related to Hy, and you can have Ey related to Hx. You can see it coming out of these relations directly. So it's just coming out of the vector notation and the vector relationships that you will only have solutions in these two combinations, and that is why when I talked about polarization, I said Ex will cause Hy, Ey will cause minus Hx. I will go a little bit more into this in the next lecture, but please revise and verify for yourselves that these equations are the way I have put them down.